Awesome.
It's just the same thing.
That's it. You got it.
Someone needs an extra.
Oh.
Ryan, he's got the left, so you can get it out there.
Alright.
Yeah. Sorry, Ryan. Down to my last comment.
Oh wait, are we gonna be given one of these on the test?
You bet. It gets attached to the final two.
Okay, never mind.
Has to be there, especially Ryan, because people have TID3 calculators, you know.
Yeah.
I have a TID4, and I don't even have the inverse T button on mine, so you bet.
I wasn't sure if we need to bring it in, because I just pulled it up on here. So.
Oh, cool, that's perfect, I like that. I like that, he's just gonna pull the thing up.
You're going to give this formulas too, right?
That's correct, all these formulas will be attached too. Awesome. All right. So we start 9.1. All right, this is 9.1, this is comparable. For a population proportion. So we don't need T for that, do we?
No.
We only use this T table for means, correct? All right, so we're looking at some problem that's got proportions in it. And this is actually, the problem I'm picking is in section 9.1, it's number 30. And it's about healthcare. And when this was done a long time ago, November 2010, so this is before the Affordable Care Act, but this was a poll given, it was a Gallup poll, and they said 493 out of 1,050 adult Americans believed it was responsible of the federal government to make sure all Americans had health care coverage. Okay, so 493 out of 1,050 felt that it was the responsibility of our federal government to ensure that everyone, all Americans, had health care coverage. This is back down in 2010. So, all right, that was the poll. And the first thing is, with this poll given, we're eventually going to construct a confidence interval about it. But the first thing I want to do, after we just have these two numbers here, is can we just verify our requirements? All right? And by me saying this is, can we just make sure that the distribution of the sample proportion is approximately normal? All right, well, is that the NPQ greater than or equal to 10? Yeah. We're going to check that. We'll just make sure that the sample size is less than 5% of the population size. And everyone, it was a random sample, so we can check that off. It was done by Gallup, and they do everything randomly. Now, when there's one thing funny I have to fix in letter A as I'm verifying requirements. Right, it's either NPQ greater than or equal to 10 or the sample size is less than or equal to 30 with means. This is the only weird thing, Art, this came up in our last lesson. This whole problem, everyone, we're doing, we're trying to estimate what's going on with the population proportion. Okay? So we don't know about this, which I have right there. That's a row. We don't know this. So in place of this, we're going to have to use the hat. We're going to have to use hats on this. That's the only thing. You go, why? Because what we're about to conduct is a confidence interval about the population proportion. This is coming from section 9.1. We don't know rho. We're trying to estimate rho. We're trying to predict it and give an estimate of what it is. So we use that in place. So to start, we got these two numbers. So where's the p hat?
493 over 1050.
Good. So as I'm going to read, p hat is equal to, this is dx, this is dn. We'll hit it on the calculator and we can write it out a couple decimal places as it goes further. Is it neat? I'm hoping. How long goes? Better write it all out. What's it come out to be?
0.4695.
I'm going to write it all out. When it wasn't a perfect 0.47, okay. 0.4695. It's roughly 47%, but I'm going to write it as 46.95%. All right. Now I'm going to check this. So n is 1,050. The p hat is 0.4695. This has come up a few times in our class. Michael, do you remember this? I write q hat. What is that? It's 1 minus this. It's just an easy way to say it. What's 1 minus, what's 1 minus a 0.4695, and I'll multiply that. 1 minus 0.4695.
.5304 or
Point 5305?
4.
Oh, because it rounded, okay, I got you. Hey, is that Harrington? I bet you're like, yep. See, this sample size is so big here, Randy. I think we're gonna be safe here. This doesn't work out when we get sample sizes of like 20. But you get sample sizes up, this is Gallup interviewed 1,000 people, this is gonna check. I was just curious what number comes on the calculator.
260.
Oh, we blew away at 10, huh, Ron? You probably saw it coming when we had this gigantic sample size. This is like 260 something, everyone check it off. Cool. Hey, is this good? You bet, everyone. You can just check that off as well. And you go, how do I know that? 5%, everyone, aren't they, they're polling all Americans? Millions. Millions. It's gonna, that sample size of 1,000 is definitely less than 5% of millions, you know? Just 5% of a million.
So you're never gonna like try and trick us and make
Exactly,
it
right.
small.
But I'll talk about that, there's some problems in, no, will not, but there's a problem. When we get to section 10.2, at the end of this whole thing, I would like to discuss something from section 10.2. There's a way to deal with small sample sizes. If you go, oh my gosh, what if I was only dealt with this small sample, I can only work with this randomly, and I did a poll, is there still a way to estimate, you know, do a hypothesis test? So I'll talk about that. But you're right, not out to trick you, exactly.
I mean, like if they describe it as normal, then you don't have to worry about it.
That's right, exactly, that's the key. We're just trying to see, is the distribution in his case, or the sample proportion approximately normal? And we just make sure the sample size is big enough. But there's a problem, and you asked a good question. Because, so we always do these checks, even teachers, you get tired of doing it. It's a little tedious to go through this thing. Okay, let me go through this. Just want to make sure the distribution is approximately normal. But in section 10.2, I didn't want you to think, well, do we just give up? There's a way we could still work a hypothesis test on a problem. If, let's say, this didn't check out for us, okay? We could deal with a small proportion. You go, well, what would you do? And Art just pointed out, he goes, the distribution wouldn't be approximately normal. We go, okay, we'll go back to the binom thing that I know Tia loves. Because I heard her ranting and raving how she loves that earlier. She wants it on the final and all that. Hey, question, go right ahead.
Never mind.
All right, cool. So we'll get to that at the end. All right, hey, so we're good to go. Now when we're going to construct a confidence interval, and you go, well, what is it? Is it 90%, 85%, 95%? In this case, everyone, you have to construct a 95% confidence interval. I'm just going to put CI. All right. Are you ready to roll? Let's go. Let's hit it. Now when I'm going to pretend like I'm in a testing scenario. This is review day. So I'm going to put myself in a testing scenario. I'm going to stat tests. And I need to know what to look up. So what kind of confidence interval is this? It's proportions, right? Don't agree? It's proportions. It's not two proportions, it's just one proportion. So I'm looking for one prop Z interval. Is that it? No, that says what?
Test.
Z-test. That's coming up in chapter 10. That's a hypothesis test. We're doing a confidence interval.
Letter A.
Letter A. All right, letter A. That's what we want. Everyone, so letter A, that's the key button. And you go, all right, I could have done this on my own, but today it's review day. We just want to see what we get. 493. Sample size is 1,050. Confidence level is 0.95. Calculate. It's like 0.439 to a 0.499. Now, when I'm going to round this to 2 decimal places, so this would be from a 0.4 what? 44 to a, what's a 499 rounded to 2 decimal places?
50.50.
Yeah, I love it, 0.50 or 0.5. And you can write CI equals, this is my confidence interval. Lowest, comma, highest, just like they write.
Are you gonna have us, what's it called, basically put that into words?
Yeah, that's coming up.
Okay.
Hey, what do y'all think? So far, so good? Yeah? Everyone good with that? All right. Leads into what Tia just asked. We got to interpret this. You know what's interesting, when I won't go through a number right now, but problems like 24 and 25 in this section, the author gave you like a question where he goes, which one of these is the right interpretation? It's not a bad idea to look at some of those problems. But we're going to interpret it right now. When we state our interpretation, we do have to reference the confidence. So with how much confidence would you go?
90%, 5%.
5% confidence.
Ooh, keep rolling. Go team. With 95% confidence. It's awesome.
The proportion.
And it's not a sample proportion, right? It's the, we're talking about, you and I are now, inferential statistics, we're now talking about the population millions. The population proportion
Is between the 0.44 and the 25.
is between those two numbers. All right, 44% and 50%. If you want to add more words, that's fine, T. You can stop your dictionary. No, I'm good. If you want to add more, you give it between what? Those who believe that the U.S. government, all right, is responsible for ensuring that everyone has health care coverage, which led into the Affordable Care Act. Yeah, I love it. Great question. She's going to write 0.44 and 0.5 out. Just don't write 0.44%, right? Mm-hmm. Cool. All right, everyone, now. We need to find the margin of error. Now I'm going to show you my way, because there's other ways. So I'm going to do my way. I'm going to go around the class. People can go, this is what I would do. So you pick the best way to get the margin of error. Now, if you subtract these two numbers here, you do get 6%. That's not the margin of error. That's, you doubled it. So I'm going to draw a picture to help you see this. There's a 0.44 over here, right? There's a 0.50 right here. But smack dab right in the middle of these two numbers is that p hat, which was that what? Like that 0.4695, which is like 0.47. He's in the middle. I'll round it to 0.47. That's in the middle. To get your margin of error, just subtract this number minus that number. And you got it. It's what is on either side of this p hat. That's why I make a picture. How far is it from there to there?
0.03.
0.03.
There you go. Now,
So you just subtract the 0.44 from the
From the
0.50.
highest,
Yep.
the highest one.
you could do this minus this. You could do this minus this. But don't do this minus this, you went too much. Cool? Now there's other ways. I'll tell you what other students do. Now they're like, that'll work, right? Does that make sense, Randy?
That
So
was-
it's from the outside part of the confidence interval to the middle. You go, well, who's in the middle? We never see it. This p hat.
Right.
The point estimate sits in the middle of this interval. Cool.
Get the .47?
Oh, we found that originally.
Oh, okay.
And here's something else. In case you forget, you'll see it on the screen. Randy, you'll see it right on the screen. It'll be like sitting right there too. You can see it if you just want to look. Because you found it at the, you go, how would I get that? You could let the calculator repeat it. Came from the x over n. Sits in the middle. So hey, that's one way to get it, right? That works every time. Not trying to confuse anybody, but Art, you mentioned something in class. You do something with these two numbers. What do you do?
Subtract them and divide by 2.
So he subtracts the whole full thing, and then he just divides by 2. That works too. You know?
So you add the 0.50 plus 0.44. and it's-
No, subtract.
See, that's why I'm worried about that. Exactly.
Subtract.
See?
Subtract 0.44 from 0.50 and divide by 2.
Okay, so you subtract both.
It's
and
not
then
adding,
divide
we
by two.
subtract.
Okay, got
That's
it.
the only thing, man. Be careful. I heard. I was like, that's the only thing.
So you take the left, you subtract left from the right one.
Right, right.
And
Okay.
divide by 2, if that helps you.
And then divide by 2.
That's happened, Randy. That's my point. It's like,
Yeah,
ah.
you know, when you do stuff like that, you know.
People think it's like an average of the two.
Yeah.
Yep. Hey, great job. Letter E.
I'm not gonna- I'll do that.
Everyone, I'm going to do this study again with Gallup. I work for Gallup. We're going to do this again. Our goal is to decrease the margin of error. What should I do?
Increase n.
Increase the sample size.
Increase the sample size. I can repeat that question so everyone heard it. I'll just go like that. Up here around. My question was, what would I do? I'm going to do this whole thing again. Same level of confidence. Everyone, I want 95% confidence. All right? But I want to decrease that margin of error, which we just saw we got. It's a 3% margin of error. We want to get this interval here kind of shrunk, right? What would I have to do? All you got to do is just increase your sample size. That's all you have to do. Costs more money though, doesn't it? Yeah, people aren't getting paid for free here at Gallup. Yeah, they're going to work. So, leads us to this question. All right. So letter F. Everyone, in letter F, what we're gonna do is we're gonna talk about, we're gonna determine a sample size. Determine the sample size necessary. Bless you. To obtain a margin of error. I'm making this up, everyone, I'm gonna pick a number smaller than this, 2%. A margin of error of 0.02. And this is with the same level of confidence, which in this problem was what? 95% confidence. All right. Now, this formula is not on the formula sheet. Let me write it here. Sample size equals P hat times Q hat all over Mo over Z squared. And this formula, though, is not on the formula sheet. So I'm just going to type all this out. You know, when I'm going to get a number, do you all agree this number is going to be more than the 1,050? Yeah, it's going to be bigger. Well, let's see what we get. All right, what goes there? I'll go up to 4 places. 0.4695. Good. Times. Times. Not plus or anything. It's a multiplication. Let's see that. Times. What was Q hat?
0.5305.
All right. And then I'm going to hit division. I'm going to hit a parentheses. This time, be careful when I'm not talking about that margin of error. We want the smaller margin of error of 0.02. There's going to be a squared here. Now this number, this is going to be a z value. I don't see it anywhere on the board. So we got to talk about that. How do I get the z right now and I'll replace it? Let me just put the yellow chalk number here because we're like, uh-oh, I don't know how to get this. And you're going to help me with this.
Inverse norm.
You got your t-tables? I recommend right now you pull out your t-table.
What will be the
So
inverse
we're gonna look
norm?
at the 95%.
Absolutely. So I'm going to use Art's method afterward.
0.2.
I'm going to start with this. You said, hold up, that's a t-distribution. Yeah, but what's at the bottom part of this table right here? Yeah. Because eventually when a sample size reached, you know, millions, you know, approached infinity, you get down to these row of z's. So go match up 95% with the z-score. What do you get?
1.960.
You got it. Now I'm going to talk about what Art just mentioned. You go, well, is there another way to get that number? And Art, could you tell everyone another way to get this number right here?
Okay, you do inverse norm,
Inverse norm button off your calculator if you wanted.
and you have to do like 100 minus 95.
I'm going to draw a picture so people see it. He's saying if you get 95% in the middle,
Yep.
you got to type into the calculator what's over there in that left tail.
0.025.
Yep. So when I'm going to put that, it'd be 0.025. This would also work on your calculator. It'll come out negative, but that's okay because we're going to square it.
Why is there a 0.02 instead of a 0.03 in
Right there, great question. In this particular problem, we know we found that for the Euler part. Let me just put a line here. I'm like, okay, we got 3% there. We said, what would you have to do if you wanted to decrease the margin? Well, you'd have to increase your sample size. So these two are kind of going together. We're saying the question goes, what would you have to do to obtain a margin of error of 0.02? So that's why we're using that. I do want to point something out though. If you accidentally did that on a test, you're going to come right back to that number. And you would probably catch it. You'd go, wait a minute. Oh, I got you. I gotta use that number. You just put yourself right back at that 1,050. This is going to be a bigger number. So if everyone okay with that, these are two ways to get this z-score. Do you prefer the table or the inverse norm button?
Can you tell me one more time how to find it on the table? I mean,
Absolutely.
I see it down
Because we
here.
get here and you go, all right, well this is a t-table. Remember the thing about the t-distribution? As the sample size just got bigger and bigger and bigger and approached infinity, which was based off the degrees of freedom, the t-distribution turned into our normal distribution, the z-distribution. So we look down at the bottom, we look at the row for z-values, but we got to line it up with all those percentages right below it. See those percentages, those are confidence intervals. And right below we look for the percentage that's 95% in the very, very bottom row. Do you see it? And right above it is the
Okay.
1.96.
Okay, I was, okay,
But if you want to look at the top, that's okay, but you got to be careful. If you look at the top row, this is the number you're going to look at. Because you got to look at what was in one tail, if that helps. So that's why I always draw pictures. Because Art does this, other students like technology. We got to be careful how to get that 1.96. All right, let's see how big this is. How big is the daggone thing? And I'm just going to go to a blank screen.
You said that formula is not going to be on the.
That's right. So it's the only one we'll just know. P hat times Q hat divided by mo over z squared in parentheses. Hey, before you leave today, see me about that too. All right. 0.4695 times 0.5305, right?
Yes.
Division. But I need a parentheses now, right, Ellen? 0.02 division 1.960 raised to the second. We always round this number up no matter what. We always round up so it's within. So can you just round it up to the next person? 2,300 and how many people?
93.
2,390. Don't go down to 2. Always round it up to the next integer. There you go. 2,393 people is the answer to the letter F. That's your sample size. Now, I'm looking. Did anybody not get that number? Well, I gotta look at your calculators. No, all right. Ashlyn, did it work?
Yeah.
Oh, sweet. Everyone's good?
So like,
Nice.
if we don't remember to round the number up, you're gonna write it like totally wrong.
50 points off.
Oh, God.
How did you get the 0.025 again?
All right. That would be if you didn't use the table.
Yeah, if you weren't using the
So what we did was, because it's 95% from the middle of this bell curve,
Oh.
so we took 100%,
Oh, okay.
subtracted 95%, divided it by 2. Cool. Some of you are like, I didn't do that, I just used the table. The two most popular z-scores, you've probably noticed. One of them's 1.96, the other one's 1.645. 1.96, isn't that close to what number? What integer? 1.96 is about a what?
2.
2. 2 standard deviations, remember that? The empirical rule? If you're 2 standard deviations away from the mean, right? 95%, yeah? Okay. All right. I got a question for y'all. Ready? We're about to talk about using t-scores and all that stuff with means. Can I raise? Yeah? All right. What is the important criteria for why we use t rather than z?
Well, the
When
sample
doing inferences
size is small.
about populations. Did you want me to write it down? They're like, yeah, you're just talking up there. All right, here it comes. I'll get this out of the way. Everyone, what is the key, like the important criteria? We're using t.
You're gonna ask that on the test? That's what I need to know. I think you're gonna ask that. You gonna ask that?
Rather than
I'm just saying. That's not much data.
the z distribution.
I don't know. No, that's general route. No, I thought they used them. I don't remember.
When performing
26.
inferential statistics. All right.
Okay, but this.
So everyone, let me just repeat this so it's clear and people go. What is the key criterion for using the t distribution rather than the z distribution when performing inferential statistics? By this phrase, inferential statistics, I'm talking about we're doing confidence intervals and we're doing population, hypothesis tests, and we'll come up with the solution to you.
First of all, I didn't know, what is the circle, whatever?
Sigma.
No, this
Oh,
one,
sorry.
so sigma.
Standard deviation.
Right.
Yeah, that's
so
sigma.
Sigma population standard, that population standard deviation is unknown. That's
Okay.
what you stated.
So this right here is the Greek letter sigma.
Sigma.
It's lowercase sigma.
Okay.
It represents a population, not a population mean, but a population standard deviation. And something had to do with this, which is the key criterion. This thing was just unknown. This was what caused the whole thing. So there's the answer. The population standard deviation is unknown, which really created this whole thing going back to that fellow named Gossett, who worked for the Guinness Brewery, right? That was the key criterion. It made us go, all right, we're going to use T rather than Z when we're doing inferential stats about a population of what? When we're doing inferential statistics about population means, okay? So, that's the answer. So everyone, we all know when we're doing all this stuff and we deal with means, we're not going to use the Z distribution, we're going to use the what? The T distribution, true? We didn't use it on my first problem. Yeah, because that was a proportion. Cool.
And that. May I get that right? I can get that question right.
Can I erase?
You said that T distribution becomes the Z distribution when N equals, what's that?
Infinity, yeah.
Right. Oh, T.
Want me to repeat it?
Yeah.
All right. You got this?
Yeah.
This is a T distribution. All right? In this left column, you have what's called degrees of freedom.
Right,
And the numbers get bigger and bigger and bigger. They're based off the sample size.
gotcha.
As the sample size, degrees of freedom also, as it approaches very, 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 very big numbers. So you and I think, what's the largest number in the world? As approaches infinity, the T distribution will actually become done, we're way, way at the end, what letter?
The Z.
Z distribution.
Okay.
Just
See,
double check that.
awesome. The T distribution changes based on the sample size, doesn't it?
Yeah.
Thanks to Gossett. See, does that make sense? Awesome. All right,
The T becomes Z when N is infinity.
9.2.
Pass.
We're going to do a confidence interval about a population mean. So I'm going to pull a problem from 9.2. I thought I'd select number 29. Blood alcohol concentration. A random sample. And this has come from 9.2. I'm taking number 29 if you're curious. I'm going to take number 29, but here's what happened. They did a random sample. Everyone hear that word, random sample? Of 51 fatal crashes in the year 2009. All right. This was the mean BAC. We're talking about the blood alcohol concentration. We all know, like, you can get in trouble if you're on the road. It's higher than 0.08. This was with the fatal crashes. All right. The mean BAC was 0.167. All right, this is in the year 2009. The standard deviation was 0.01. All right. And how many crashes was it?
51.
51. All right, Owen, do you see mean?
Mhm.
All right, this was a sample mean average. Those are the mean numbers. Standard deviation 0.01. 51 fatal accidents. But this is mean, so we are going to have to consider in this problem here, Sierra, degrees of freedom. So I might as well write it down. What's DF?
51.
Yeah.
N minus.
N minus 1. Don't agree?
Yeah.
So I might as well write it down, since I know I'm dealing with what? Means, right? We're going to use the T distribution. We'll use this. We got means, but I might as well write it down. Degrees of freedom, you got 50 degrees of freedom. All right. Anything else? Well, that's gonna come up, they're gonna say what confidence interval they want. So, hey, letter A, can you verify requirements? Now this time, everyone, this is not the MPQ greater than or equal to 10. In this problem, everyone, because we're dealing with means, if we want to ensure that the sample distribution of that sample mean, you know, if the distribution of the sample mean is approximately normal, the sample size has to be greater than or equal to 30, is it?
Right.
All right, we're good. Is it a random sample? Check. Let's roll. Whoops. Woo. We got a random sample. We're rolling. Everyone agree? Can the sample size be smaller than 30? It can if they have knowledge about the population already being normally distributed. Okay? So don't get thrown off there, Mia, when you think, are they trying to trick me? Sometimes in a problem, you go, is the sample size greater than or equal to 30 or this stuff? You go, if it's not greater than 30, I stop. Well, if it's sample size like 20 or 15, maybe they said they have knowledge of the population already. Like with gestation period, where we already know that the distribution for the gestation period for the population is already approximately normal. Then we don't have to worry. Does that sound good?
Yeah.
But you'll see that on the check. I wrote that. I put that down that, you know, who cares if your sample size is really small if you already know that the population, all right, not sample, but the population is normally distributed. All right, letter B, when you're going to construct, this time not 95%, a 90% composite. All right. Where are we going? Hit it, everyone, hit it! Hit it! Hit it! Hit it! Hit the calculator. Where are we going? Clear?
Number 8.
Is it number 8? I'm hearing 5, 6, 8. Who is it? Is it a test or an interval? Is it a test or an interval?
No, this is not a test, it's interval, number 8.
Interval, right?
I don't know.
Wait a minute. Construct a 90% what?
Interval.
Right? Confidence interval. True, right, everyone? No, but this can happen. You're like, I don't know. This is what I'm going to talk about. You go, it says confidence interval. We're looking for interval. All right. So we're going to go in here. I don't see it yet. There it is. And when it's a T interval. We're going to use a T interval. All right. Now, am I using data? That would mean they give me data out of the textbook, and I got all the end of the data in L1. No, I already have my statistics, right? So I'll make sure that's highlighted, and all this pops up. Okay, what was X bar?
0.167.
Okay, 0.167. That is a high blood alcohol concentration. What's SX?
0.01.
What was the mean? Then again, these are the fatal crashes. This is 51. What's confidence level?
90.90.
0.90, which is 0.9, and I hit calculate. All right, what is it?
0.164.
This time I think I'll go out to 3 places.
Okay.
0.165,
And
169. You know? Boom. 0.164, 0.169. All right. Hey, anybody want to interpret that?
Yep. With 90% confidence,
Okay, with 90% confidence.
the population mean is between, with
The population mean. Ah, I love it. Not the sample mean. We know about the sample mean. The population mean.
is between,
And then when you come up with the fatal accidents, what alcohol is involved,
we don't need to write all those stuff, right? Like,
that's right, is between.
0.165 and 0.169.
You got it.
Hey, what do you, we don't have to write what?
He wanted to know if you want to put more wording. You can if you want. You want to be like,
The people who are.
oh, the people, good point, Tim. Oh, the blah, blah, blah. You go back to it. Hey, I'll be honest though, if you were taking like an advanced placement exam, where, you know, they put a bunch of graders out in like Colorado and they sit there for a week and grade all exams, I would be like, yes, write that. You follow me? I would be like encouraging you to write that. Does someone want to hear about all that stuff? But here we're good with 90% common population mean. What's important to me is we're talking about not the sample mean, the what?
Population mean.
Yeah, we're talking about, lots and lots and lots of people here. And in the end, when you go, I still don't know what this means. What we're saying is that if I took 100 more of these samples, all right, this is what I mean. 90 out of 100 of them would come up with an X bar between these two numbers. That's what it means. So if you really want to know what that means, you can even write that as an interpretation. If I did 100 more samples, just like this, 90 out of 100 of them would get a X bar that came out to be between this number and this number. That's what I'm saying. So we're really, really confident it's in here. Excellent.
Okay, so when we did 9.1 and we were constructing the percentage, and on the calculator we did 1 minus whatever prop z.
Yeah!
So why do we?
Didn't have to do it here, did we?
We did.
It's a different check. I know. Now you're doing about this thing, right? You're doing about
No,
one.
I'm talking about when we were on B.
So letter B, when we did that in 9.1, we just used the technology, you agree?
Yeah, right. But we went through a different.
Yeah, we did the formula first.
Oh, absolutely. You're right. It was a one proportion Z interval. Now this is for means. It isn't a proportion.
Okay.
And we call it a T interval, right? Because you remember with mean, Mr. T, mean, we're going to use T.
Okay.
So very good point. Hey, in your notes, 9.1, who was the cool button? It was really letter A. But in 9.2, with these means, the cool button was number 8.
Right.
Cool?
9.2 is dealing with population.
Right. 9.2 dealing with population mean. We think T. So very good point. Hey, D. Everyone, I bet you know how to get the margin of error. But use your favorite way. Randy, use your favorite way. Everyone use your favorite way to get it.
Hold up.
See what we all get.
What happened?
The margin of error.
Okay.
I'll draw a picture. I'm going to draw a picture. I'm a picture person. Oh, there's the interval. Who's in the middle of the interval?
1.167.
I just need that part. One side. That's my margin of error.
0.002.
Bam. Very small. That's really small. Hey, let me ask it again. Hey everyone, if we did another poll study with the same level of confidence, and we wanted to decrease the margin of error, what would I do? Increase the sample size. Question?
Would it be the MOEB plus or minus?
I love it. I'm going to
Yeah.
put that. You can just write this, but she's right. She goes, you always put a plus or minus. Even the literature that you read this stuff on the internet, they put that plus minus there as well. Right? Very good. Hey, what should I do if I wanted to decrease the margin of error and do another study like this, same level of confidence? Increase the sample size. Jack up N, right? You're going to need more of these fatal accidents randomly to report and come up with your statistic. Can I erase?
Oh, so we have A to E for 9.2?
Can I erase?
Mm-hmm.
Rocking and rolling, everyone. Rushing it. Hey, there's some good practice problems in that book. As we do this stuff, I do want to point out 9.1, Brianna, remember when we did this like letter F, determine the sample size thing? When you practice a problem out of the book, if they say there was no prior estimate, that just means for your p-hat, use 0.5. Okay? Has everyone got that? There's good practice problems in the book, right? I mean, do them. But when they go ahead, there was no prior estimate, and you're trying to determine the sample size, just use p-hat at 0.5. Which means, what would q-hat be, Michael? If p-hat's 0.5, then q-hat will be a 0.5. All right, 10.1, this is just intro to hypothesis test. So I'm going to read something from the book, and you're going to help me just set up the hypothesis test. It'll be quick, but let me read it to you. I'm in 10.1. All right, which one's good? Okay, this is number 17. It's in 10.1. I need you to set up a hypothesis test. Well, we might as well get it ready. When you set it up, you put the H naught and you put the H1, right? Yeah, we're just gonna set this thing up. But you gotta determine whether you're gonna use mu or the rho, okay? Rho looks like P. Some students call it a P, that's fine. According to the National Association of Home Builders, the mean price of an existing single-family home in 2009 was $218,600. Let me write that number down. 218,600. That was the mean value of a home in the year 2009. Which symbol? Man, you're good. I don't see a percentage, do you?
Right.
Equals. This is the same letter. This is the same number. What goes here? You say, Professor Messer, you got to continue reading. Okay, let me continue reading. The next sentence says, a real estate broker believes that because of the recent credit crunch, the mean price has decreased since then.
So I should.
That dictates the whole test. We want to do this test. They just wanted to set us up. There's something else they wanted you to do on this problem. Everyone, we need to explain what a type 1 error is. Alright.
Can I ask you a question?
Ooh, good, Art.
Would it be okay, like on type 1 error and type 2 error, we just explain the way you explain it? Because in the book they wrote a big love story.
Absolutely.
The love story.
I love his point. He goes, he did it like a love story. He's right. So, Art, no, you do not have to do it like the love story like the other book. What would you say here? And just keep it nice and simple for the class. Watch
Okay,
this.
the HO is true, but
Alright.
the researcher rejects it.
Perfect, that works. No, and I'm gonna put a little phrase here, hot, because hasn't it been hot out lately? That's just this is my little phrase, hot, just to help you remember this. Type 1 error, I gotta write this in words though. All right, hot, and I'm saying, explain what a type 1 error means, hot. What do I mean? Well, the null hypothesis is true. It's actually true, this is what Art was saying. And the researcher, in this case, it was a real estate broker, but I'll just say, you know, the real estate broker, he or she is a researcher. The researcher, you know, mistakenly did what?
Rejects it.
Rejects it. Done. That's what's going on. That's what it would mean to make a type 1 error. It's not a big deal, but when it happens. Students are always curious about this stuff. They always go, what's the error? It could be a number of things, a lurking variable and stuff. Stuff you're not aware of. I always say Gossett, remember Gossett at the brewery? He kept making type 1 errors. He knew something was up. He's like, what's going on here? Well, he was using the Z distribution. He had to invent this T distribution for the small sample sizes dealing with means. He kept making type 1 errors, right? He kept what? He kept thinking, oh, I was rejecting this, right? He was mistakenly rejecting what he had. He had a good quality beer there, right? He's like, what's going on? No hypothesis was true. All right, can I erase? That's a good phrase to help you remember because it says HO, that means HO what? True, and then you made a mistake. What would be the mistake? Well, I guess I rejected it, right? Cool. All right, perfect. We got time for 2 more problems. 10.2, 10.3. Oh, and I like to do 10.3 first because I like to deal with means first. Sorry. So let's do it the one with means. So 10.3. Then we'll finish up with 10.2. And then Brianna will talk about that small sample size. Oh no, it was me who asked about that. We can talk about that at the end.
So if you ask a 10.1 question, is it just gonna be just like that, like?
Yeah, 10.1 is a funny section. Like not every stat book does this, where they just do an introduction to hypothesis tests. It's kind of short, sweet. They just want to make sure you know how to set them up, right?
Are you
And then be able to interpret that. So that's all we're doing in that section. You bet. That's it.
Are we gonna have to explain the type 2 error also?
No, just type 1 error.
Oh.
Type 2 error would be the opposite, Mia, if you're curious. You go, what would that be? Oh, the H1 would be true.
And they mistakenly.
They do not reject the null. But I will. I like type 1 error. I like to hit on that. All right, this is 10.3. Everyone, I'm going to do number 15. This was effects of alcohol in the brain. Okay, more with alcohol. Okay, we got this. What's interesting in this problem, everyone, they start out, they give a sample size, you know, they just want to measure the effect of alcohol in a certain region of the brain, and their sample size, I'm going to hit it right away, was this. So I'm sure that alarms a lot of people. It's the first thing you spot in this problem. I mean, there we are, we're sitting with 12, and we're like, hold up, this means sample size has to be greater than or equal to 30, right? But I'm going to go further down this word problem because it's this long. And they make this statement, all right, and they said that it was approximately normal, all right? Analysis of the sample data revealed that the volume is approximately normal. So by them saying that, all right, analysis of the data said it's already approximately normal, we're okay with this check. Does that make sense? So we're okay that this isn't greater than or equal to 30. So when we do this problem, I do want to point out when we do our verify requirements, we're okay with because of that statement. All right? It was way down the word problem though, Brianna. They said, an analysis of the sample data revealed that this certain volume is approximately normal, and they give the sample size and the standard deviation. Cool?
So when they say it's approximately normal, then you don't have to do the checks because they're telling you that it is.
Yeah, they already checked it out for you.
It's
You're
already
right. Sample size wouldn't have to be greater than or equal to 30.
Okay.
It could be, like in this case, 12.
Okay.
So very good question. This is what means. So let me give you all the numbers they get from this problem. Edwin, so they got, this is the effects of alcohol in the brain. Let's see, the X bar is 8.10. That's the sample mean, right? The standard deviation, the sample standard deviation is 0.7. All right. And I'm going to change colors. What's the alpha level? All right, this is totally different. I pull out this yellow chalk, right? They call this the level significance. 1%. See, usually when you get in this field with, you know, things like this, they like to be very, 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 very serious about this. And they consider anything less than 1% aren't rare or unusual. That's what we're looking at here. Anything less than 1% is unusual. All right? So now, anything else? Well, you got to set up your hypothesis test. All right? What else do we have to do? Verify requirements. Then we're going to justify our results by doing two things. We're going to do the classical approach. And the p-value approach. And then after that, when we are going to make sure we state our conclusion. Sound good? All right. Now, everyone, here comes that first sentence. They want to determine whether or not, they said everyone, in the null hypothesis, the null hypothesis, they're stating in the first sentence, because they always put that first, is 9.02 cubic centimeters. 9.0 cubic centimeters. So that's our status quo. So when I set up this, so when this is means, right? 9.02, this is a portion of the brain, and they're talking about volume, so that's why it's cubic centimeters. It's just a certain portion of the brain, all right, that they were looking at and studying. But they said the population, you know, mean was 9.02 cubic centimeters. That's a mu, right? All right. If you want to put cubic centimeters, you can. Yeah, but what did these researchers believe? All right, they wanted to determine whether it was less than this. They wanted to determine, the research wanted to determine whether it was less than that volume of 9.02. What's simple? Less than? Awesome. Same letter though, right? Or parameter. Hey, verify requirements. Verify the requirements. Uh-oh. But what did the book say?
Simple random sublet and normal.
Yeah, so we can check this off. There you go. It was only 12. Yeah, but remember what they said? Sample data came from something that was already approximately normal, so we're good. It was a random sample, so we're good there. Now, Did this? Let's perform the classical approach. This is where we draw a bell. All right. Whoop. Whoop. I like to remind myself here, Autumn, am I using T or Z?
T.
Because of that. Because it's population means T distribution. Right? Mean Mr. T. Yeah, mean Mr. T. I'm using T, right, everyone? Mean Mr. T. I'm thinking T. I'm going to use the means. I'm going to use this T distribution. Which leads us right to this table. When you get your table, unless you got an inverse T button. Excel has that inverse T thing if you want to use that, Ryan. I feel like Excel does have it, but I just use the table.
Don't you need to do the DF thing? Like
Yeah,
degrees of freedom?
I love it. So where am I shading?
On the left.
On the left.
I love it. Because of this, we're shading here. How much? Just 1%. How much? Left tail test, they call this. A left tail test. Left tail test. All right. Rocking and rolling. I need to get what's called my critical value. Is it a Z crit or a T crit? It's a T crit. We call it our T crit. Is it going to be positive or negative?
Negative.
So I'm going to get it ready and put a negative symbol because it's on the left side. Does that make sense? Are you sure? Like T equals 0 here, but T is negative on this side. This table doesn't have any negatives on it. Now, how do you read this thing? It's something about the DF. And I didn't even write down DF. What's DF for this?
11.
Right, Mia? They said sample size 12, so I'll put it right here. The DF, degrees of freedom, is 11. 6 donuts, 5 degrees of freedom, right? So I'm going to look for 11. Is there 11 on this left side?
Yeah.
Where are you matching it up with, though?
0.01.
So look to the top. Is it 0.1 or 0.01?
0.01.
All right, look for 0.01 with 11.
2.718.
2.718. Make it negative, though, right, everyone? Now, some people go, I've got a cool new calculator. Well, then you'd have to hit inverse T, 0.01, comma, 11 on your calculator. And it'll give it to you. That's if you got, I don't know if you have that, Randy.
Yeah.
Oh, he does. All right, that's what you do. Make sure you put comma and degrees of freedom. We don't have it. My lame calculator doesn't have that cool inverse T button.
-2.7.
Ah, it sounds like we're good then, huh? Our table's just as cool as his new calculator. Hey, when there's something else to finish up the classical approach, we need something called the sample test statistic. All right? I am dropping that yellow chalk. I don't need it anymore. So now I'm going to compare this to something called the sample test statistic. The reason I'm writing this on the board is because sometimes people get these two things confused. I've got the white chalk, right? Where's this number come from? We'll get it from the calculator, but it's coming from these sample measurements, right? Where did this number come from? This number only came from what? This T crit only emerged from the 1%. Does that make sense? So if you like to color code like me, pen, pencil, cool. It's time for the what? We're going here, right? All right, let's go. Now this time, Brianna, I'm not going to do any more intervals. This is a test. So I'm looking for a test. But it's not Z's, it's not the proportion stuff, it's a T type of test. So let's find in that group
Number 2.
T test. And Art says number 2. Who comes up for it? Hey, and here, Brianna, I want to show you, remember this was A, this was 8? 10.1 was just intro, but what do I use in 10.3? Number 2. No one see that? Keep this organized. Let's save it. What do we get? Stats? What's this number? 9.02? What was X bar? 8.1? Standard deviation? 0.7? Sample size? A mere 12. Which symbol? Less than, calculate. Awesome. Someone see it? What is it?
Negative 4.55.
I'm gonna have to hit the light so we can put this in the picture. I'm wondering whether or not this is in the critical region.
Yes, it is.
Is it in there?
Mm-hmm.
Do you all agree it's in the critical region? That's that shaded region I did. Is that number in here? We should mark it. Where is that? This bell kept going.
Follow it, yeah.
It's probably about right here, right? There it is. There's P naught. Let me continue shading with my yellow. Is it in there?
Mm-hmm.
It is. And when this is in here, we reject the null, right? What was that number? Negative 4.55?
Yeah.
I'm just gonna leave myself a note. We already know the answer. We're rejecting what? This is what I'm doing with this problem. We're saying, hey, you're out. We've got evidence for what? For this thing. So can we state the conclusion?
Yep.
All right, Owen, I'm already gonna state my conclusion. Because I know it. What's my conclusion? I already know it.
There is evidence suggesting that mu is the
Do you want to be like the author? There is sufficient evidence. There is evidence. Suggesting I always state this. Brianna, I always state this alternative. So there's evidence that mu is less than 9.02 cubic centimeters. Is that cool? But then we're going to do the p-value first. So how do I get that p-value? Oh, it's on the screen. What was it? Someone see it?
4.123.
Over T.
Everyone look at this p-value and watch what I write on my board. P-value. This is perform the p-value approach? Okay, do the p-value approach. Well, the first thing is when we do the p-value approach, we report the p-value. Watch what I do. The p-value. Everyone, I'm telling you, I'm probably going to see this on 10 papers on the next test. Look what I wrote.
Good you.
At least 10 pieces of paper will have that.
That's not right.
And T goes, that's not right. I'm telling you, really? I'll have up to 10 students do this. It's probably because it's not highlighted where? Way at the end. See it? It's almost like we wish a bright light shined here. Or like a blinking light showed up. That's not 4.13, that's 4.13
times.
10 to the negative 4, right? 4.13 times 10 to the negative 4. Now you can write it like that. Some of you write that in decimal form. What is that?
0.004.
With 3 zeros and then a what?
4.
If your p-value is low, reject the ho. If your p-value is low, reject the ho. Is that p-value lower than 1%?
Yeah.
Yeah. That would be extremely unusual.
Another way to
And
consider.
yet we got it, so we're rejecting the null hypothesis. So here comes my interpretation of the p-value.
You are not doing the TCDF thing.
You can if you want. This was a faster way.
That confirms it.
That's exactly what does it. So he does a TCDF and he confirms it. Very good. That would actually confirm it. Very good. All right, I'm going to interpret this. And this is the probability. See, a p-value is a what? It's a probability.
Mhm.
This is the probability of obtaining these results. I'll show you what I mean. These statistical results. You go, what do you mean by these statistical results? I'll show you, I'll put it in parentheses. We just found the probability that this x bar, was it greater than or less than? Look at the picture. It was that way, right? We're saying, what was the probability that x bar was less than or equal to that what? 8.1. And here's the most important part when I interpret the p-value. This was all based off what, though? Not some magic number. Everything was based off this thing. So when I say this, I go, this is a probability of obtaining this. And then I go, if mu is, and this time I'll emphasize that, if mu is really, truly, how much?
9.02 centimeter.
9.02 cubic centimeters. See, it was based off that null hypothesis, right? This is the odds of getting this. But I mean, wouldn't this be kind of unusual in this world? That's extremely rare. That's extremely unusual. So because the p-value is lower than the alpha level. All right, I'll use the yellow chalk. What was alpha? 0.01, what was our p-value? 0.0004. What am I doing with this null
We
hypothesis?
reject.
We reject the hoe. If your p-value is low, reject the hoe. Just don't write that. Just don't write that. Y'all are doing awesome.
So on this, interpret part, we need to write that whole thing.
Yeah, you want to know what's the hardest thing for students? Not just go with Professor Messer, across the nation, is students interpreting a p-value. You know, it's not that bad though. You can just go for it, you know? It's based on the results. The key thing about this, when you say it, a p-value, it's a probability, right? Of getting these results that we got, right there, or more extreme. We say or more extreme, that's why I did this less than symbol. Based on what though? So I wrote if, based on if, that's the given value, the given population proportion. And then because what? You look at your p-value versus the alpha level, you compare them. And if your p-value is lower, what do we do? If your p-value is low, reject the, what if it was greater than? We fail to reject the null hypothesis. We fail to reject the hoe.
So in the conclusion, we state the alternative hypothesis.
Always.
In interpreting the p-value, we state the null.
That's right. That's exactly it. Isn't that cool? Hey, one more thing before you leave. I still want to do a what? Which section? 10.2. The most important thing is, I know you can run through the numbers, is I wanted to make sure right before you leave, we have time, is set up a bell, right? And I want to make sure you split up that alpha level when it's a two-tailed test. Okay? Let me make sure you're okay with that. We don't have to run through all the same stuff and all, but I want to just get that set up. Does that sound good? So, I'll erase this. That one in 10.2. This problem was about, you're going to laugh, it was about men's strain during marriage. So they did a poll, everyone. First of all, this is according to men's, it's like mensstuff.org. They said 22% of men have strayed during marriage. Okay, 22%. Is that a mu or a rho?
Row.
Okay. 0.22. But then they said this. This is in section 10.2. A researcher believes that number has changed since then. Did you hear the wording?
Mm-hmm.
Has changed. Well, it hasn't gone up or down, so it's what?
Not equals.
All right. Well, the level of significance in this problem, I'll tell you the sample they did. They took a sample. The only thing about this, everyone, we're smart. Don't do the checks on this problem, but would you think about this, the bias involved? Can't people lie in a poll? I mean, what if their wife's standing right next to them or they're on the phone? They're like, worried someone's listening. They're like, no, I never did. You know, so that's the only thing about this and this infidelity. That's what they titled this. But here's the sample they got. 122 out of 500 said they strayed at least once during marriage. And we're going to do this problem with an alpha level of 0.05. All right. Oh, do you want the problem number? This was number 24, actually, I was taking from that section. What's so important to me before you left is when you set up your classical approach, we'll hit it on the calculator. When I set this thing up, I make this bell. We're using Z because it's proportions. How do I deal with this to get my Z crit?
Oh,
Both sides.
So do I shade 5% here?
No. 2.5.
What is half of 5%?
0.025.
And all you did was cut this in two, right? Right. Is that okay with that? Because of this, what are they doing? They're taking alpha level divide 2. Now, this isn't a T crit, but it's called a what? How can I get it with that T table? Does anybody know? So you can use inverse norm like Art does. Inverse norm 0.025. But maybe you don't want to do that. If you don't want to do inverse norm 0.025 on your calculator, how can you use that table to find it?
You look at upper tail probability.
look up at .025 at the top, right?
Yep.
And then go-
We won't look at .05 though. What do you get for Z? It's that number comes up over and over and over again. What is it?
1.96.
So this one's negative, and this one's what? So when, we don't have to write everything down this time, but I want us to concentrate on the p-value. We're in the last button. Perfect time, and this is from 10.2. The button we're looking for is a one-prop z-test. One-prop z-test. Where is it? It comes up fast. It's not number 2 though.
Number
It's number 5. One-prop z-test. Okay. Where when you and I are going to concentrate on the p-value, right? If your p-value is low, what are we doing? You go, how low? Well, lower than a 5%. Well, let's see. So I go in here, here's my one-prop z-test. Not interval, z-test. Me, I'm going to put the what? The 1, 2, 2 thing they got. This was out of how many people? Whoops. What was the null? He said it was 0.22.
Yeah,
122, this was out of what?
500.
500. What was, oh, it's a two-tailed test because has changed, right? Lock it. I like calculating. I'm looking at p-value. I want to know the end of the story right now. Am I rejecting the hoe? Where's the p-value? Not that, that's the p-hat. That's the p-hat, right there. That's like 20% chance.
Yeah.
That's not very low, is it? Do things in this world happen with 20% chance? I think there's like a 20% chance of rain today. I'm thinking of mowing my lawn, but you know, that could happen, right? I see clouds and stuff, it could rain. So, are we rejecting the hoe? No. In this problem, we do what? We do not. We do not reject
We
it.
can't keep it.
But we can't keep it.
So we would reject, we would fail to reject,
Well, listen to her wording. She goes, we fail to reject the hoe. If you like it like Sierra, that was good, Sierra.
so we fail to reject her because P is greater than the, alpha level.
Yep, that'd be right down there at your interpretation of the p-value. You'd say because your p-value was what? Greater than the alpha level of significance, we fail to reject the what? Oh. So hey, can I just state the conclusion in words? There is not evidence suggesting that rho is different from 0.22. Y'all agree? Somebody go with that? I'll say it again. My conclusion? My conclusion? There is not evidence that rho is different from 0.22.
And then we can say because.
Because nothing's wrong with
Because you do.
Oh yeah, make your conclusion short. Look, there is not evidence suggesting what? Now, interpretation of the p-value. Colin was talking about my interpretation of the p-value. Because my p-value was higher than the what? Higher than this, we fail to reject the. Good job!
No hose.
Let's play keto.
I'll get it.